Biogas is produced through the anaerobic digestion or fermentation of organic matter. It primarily consists of methane, carbon dioxide and small amounts of other gases such as nitrogen, hydrogen sulfide and traces of moisture. It involves the decomposition of organic materials in the absence of oxygen, typically in a biogas digester or an anaerobic reactor. This organic matter includes agricultural residues, animal manure, food waste, sewage sludge, and energy crops. During the anaerobic digestion process, microorganisms break down the organic matter and produce biogas as a byproduct. The methane content in biogas makes it a valuable energy source that can be used for various applications. Biogas can be combusted to generate heat and electricity or purified to remove impurities such as carbon dioxide and hydrogen sulfide, resulting in biomethane. Biomethane can be directly injected into the natural gas grid or used as a transportation fuel for vehicles. It helps to reduce greenhouse gas emissions by capturing methane, utilizing it as a renewable energy source. The use of biogas contributes to the reduction of air pollution and dependence on non-renewable energy sources. Hydrogen fuel cells are devices that generate electricity by combining hydrogen, H2, and oxygen, O2, through an electrochemical process. They operate based on the principle of converting the chemical energy stored in hydrogen into electrical energy, with water as the only byproduct. Fuel cells are part of the broader field of hydrogen energy, which aims to utilize hydrogen as a clean and efficient energy carrier. Hydrogen gas is supplied to the anode of the fuel cell. The fuel cell contains an electrolyte, which can be either a polymer membrane or an alkaline solution. The electrolyte allows only protons to pass through while blocking the flow of electrons. At the anode, hydrogen molecules dissociate into protons and electrons. The electrolyte allows the protons to pass through to the cathode while forcing the electrons to take an external circuit path. As the electrons flow through the external circuit, they generate an electrical current that can be used to power devices or charge batteries. Oxygen gas from the air is supplied to the cathode of the fuel cell. At the cathode, oxygen molecules combine with protons and electrons that have traveled through the external circuit. This reaction produces water as the only byproduct. In addition to producing electricity, fuel cells generate heat as a byproduct. This waste heat can be utilized for various purposes, such as space heating or water heating. Hydrogen fuel cells have several advantages. Fuel cells can achieve higher energy conversion efficiencies compared to traditional combustion-based systems. Clean and zero emissions. Fuel cells can be scaled up or down, making them suitable for a wide range of applications, from small portable devices to large-scale power generation. Energy storage. Challenges associated include the production, storage, and transportation of hydrogen, as well as the cost and durability of fuel cell systems. Ocean thermal energy conversion is a technology that harnesses the temperature difference between the warm surface waters and the cold deep waters of the ocean to produce electricity. OTEC systems utilize warm surface water, typically around 20 degrees Celsius to 30 degrees Celsius, found in tropical or subtropical regions. The warm surface water is pumped into a low-pressure chamber called the evaporator. In the evaporator, the water is heated and its temperature is increased further by using a low boiling point working fluid, such as ammonia. The working fluid evaporates due to the temperature difference, creating high-pressure vapor. The high-pressure vapor produced in the evaporator flows through a turbine, causing it to spin and generate electricity. After passing through the turbine, the vapor is condensed back into a liquid state by exposing it to cold water. This cold water is drawn from the deep ocean, typically from depths of about 800 meters or more. The cold water absorbs the heat from the vapor, causing it to condense and return to a liquid state. The condensed working fluid is then pumped back to the evaporator to repeat the cycle. The heat extracted from the vapor is transferred to the cold deep water in the condenser, which is discharged back into the ocean. Benefits. Renewable and clean. Provide a consistent and stable source of electricity. They can provide a source of cold water for air conditioning, desalination, and aquaculture, as well as support the growth of certain marine organisms. Challenges. High capital costs. Limited geographic suitability. May have environmental impacts, including the discharge of cold water into the ocean, potential effects on marine ecosystems, and disturbance to seabed sediments during pipe installation. Technological challenges. Wave energy involves the conversion of the kinetic energy present in ocean waves into usable electrical energy. Wave energy conversion devices are deployed in the ocean to capture the energy from waves. When waves pass through the WECs, they cause mechanical motion or pressure changes. This captured wave energy is then converted into another form of energy, typically mechanical or hydraulic. The converted mechanical or hydraulic energy is used to drive a generator or hydraulic system, which produces electricity. The electricity generated by wave energy systems is converted to a suitable voltage and frequency and then connected to the electrical grid for distribution and consumption. Wave energy offers several advantages. Renewable and abundant. Environmentally friendly. Predictability. However, there are challenges associated with wave energy. Technological maturity. Harsh ocean environment. High costs. Impact on marine ecosystems. Tidal power, tidal energy, utilizes the natural rise and fall of tidal waters caused by the gravitational forces of the moon and the sun. Tidal barrages are large structures built across tidal bays. They feature sluice gates or turbines that allow water to flow in and out during tidal changes. As the tide rises, water is stored behind the barrage, creating a potential energy difference. Tidal flow turbines are submerged in the tidal waters. They are designed to capture the kinetic energy of moving tides. The turbines are typically positioned in areas with strong tidal currents. As the tide starts to recede, the water stored behind the tidal barrage is released, flowing through the turbines. The movement of water drives the turbine blades, which are connected to generators, producing electricity. The electricity generated by the tidal turbines is then converted and transmitted to the electrical grid for distribution to consumers. The advantages and disadvantages are similar to wave energy. Geothermal energy utilizes the heat stored beneath the Earth's surface to generate electricity. Geothermal energy potential is assessed by studying the geological characteristics of an area to identify regions with suitable conditions for harnessing heat from the Earth's interior. These conditions include the presence of hot rocks or reservoirs and permeable pathways for fluid circulation. Geothermal wells are drilled into the Earth's crust to access the geothermal reservoirs. There are several types of geothermal power plants. Dry steam power plants. In areas where high temperature steam is present, it is directly used to drive a turbine connected to a generator, producing electricity. Flash steam power plants. In areas with high pressure hot water, the water is passed through a separator, where pressure reduction causes it to flash into steam. The steam then drives a turbine connected to a generator. Binary cycle power plants. In areas with lower temperature resources, hot water or steam is used to heat a secondary fluid with a lower boiling point, such as isobutane or pentane. The vaporized secondary fluid then drives a turbine to generate electricity. Biomass energy refers to the energy generated from organic matter, such as plants, agricultural residues, forestry byproducts, and organic waste. Biomass feedstock can come from a variety of sources, including dedicated energy crops like switchgrass or miscanthus, agricultural residues like corn stalks or rice husks, forestry residues, or organic waste such as food scraps or animal manure. Biomass can be converted into energy through several processes, including combustion, gasification, pyrolysis, or anaerobic digestion. Combustion. Biomass is burned in a controlled manner to produce heat, which can be used directly for heating applications or converted into steam to drive a turbine connected to a generator, generating electricity. Gasification. Biomass is converted into a combustible gas mixture known as syngas by heating it in a low oxygen environment. The syngas can be used for power generation or converted into liquid fuels or chemicals. Pyrolysis. Biomass is heated in the absence of oxygen to produce biochar, liquid bio-oil, and syngas. The bio-oil and syngas can be used for heat and power generation, or upgraded to produce transportation fuels. Anaerobic digestion. Organic waste, such as food scraps or animal manure, undergoes a decomposition process in the absence of oxygen, producing biogas, which consists primarily of methane and carbon dioxide. Biogas can be used for heating or electricity generation, and the residue left after digestion, called digestate, can be used as a nutrient-rich fertilizer. Hydropower, also known as hydroelectric power, is a form of renewable energy that harnesses the energy of flowing or falling water to generate electricity. A dam is constructed across a river to create a reservoir, which stores a large amount of water. The dam helps control the flow of water and creates a height difference, known as the head, between the reservoir and downstream. Water is drawn from the reservoir through an intake structure and directed into a large pipe called a penstock. The penstock carries the water from the reservoir to the power plant. As the high-pressure water from the penstock flows through the turbine, it causes the turbine blades to rotate. The turbines are connected to generators, which convert the mechanical energy from the rotating turbine into electrical energy. After passing through the turbines, the water is released back into the river downstream. Wind power involves using wind turbines, which are tall structures with large rotor blades, to capture the energy from the wind and convert it into electrical power. Wind turbines consist of three main components: the rotor, the nacelle, and the tower. The rotor includes 2 or 3 blades mounted on a hub. As the wind blows, it causes the rotor blades to rotate. When the wind blows, the blades spin. This rotation converts the kinetic energy of the wind into mechanical energy. The mechanical energy from the rotating blades is transmitted through the shaft inside the turbine's nacelle. The nacelle contains a gearbox, which increases the rotational speed, and a generator, which converts the mechanical energy into electrical energy. Solar power is a form of renewable energy that utilizes the energy from the sun to generate electricity. Solar panels are made up of multiple solar cells. These cells are typically made from silicon and have a thin layer of semiconducting material that converts sunlight into electricity. When sunlight strikes the solar cells, it excites the electrons in the semiconducting material, creating a flow of electrons. This flow of electrons generates direct current electricity. The DC electricity produced by the solar panels is then sent to an inverter. The inverter converts the DC electricity into alternating current electricity. The AC electricity is transmitted through the electrical panel and distributed to power the electrical devices and appliances within the building. If the solar power system generates more electricity than is needed, the excess power can be sent back to the grid for credit or stored in batteries for later use.